All right, so we are looking at nutrients ingestion to energy metabolism. So we're basically going to, the purpose of tonight's lecture is kind of to track all of our macronutrients, right? And all of our micronutrients. We're just tracking basically everything all the way from, when we get it into our body to where it starts actually like producing energy, right? Producing metabolism. So that's going to entail talking a little bit about the digestion of everything again. So it's going to feel pretty similar to when we talked about digestive system physiology in our last class. And then we'll talk about like how that's used to actually produce energy, which will also feel somewhat similar to our last class. So we will kind of review the digestive system here in the beginning. So today we want to talk a little bit about like what happens to nutrients after they're ingested, how they are absorbed, how carbohydrates are absorbed, how fats are absorbed, and how proteins are absorbed. We also want to understand like how vitamins, minerals, and water are all actually also absorbed and then metabolized by the body. What is metabolism? What's energy? And then how do we actually do that to produce ATP through our various metabolic pathways? So I love this because it's like NASM's addressing my favorite concept, which is like nutrients are said to be outside the body until they are absorbed across the membrane through the linings of your digestive tract, which is a big fancy way of saying you are a human donut, right? Like that's what we're saying. Like you're a donut, right? You're going to bring food into your body, but it's still outside your body until it's digested small enough to pass through the wall into your bloodstream. Now it's in your body, right? So we got to treat our digestive tract kind of like the outside environment in a way. So once our nutrients are absorbed, they're transported throughout your bloodstream and also in your lymphatic system, which is basically like a series of tubes transporting water throughout the body. That's like your lymph nodes and things like that. And so like then those nutrients are going to get wherever it is they are going in order to be able to do whatever it is they need to do. If they're carbohydrates, they're probably going to be used for energy, or if they're fat, they're going to be used for energy, and if they're protein, they're probably going to be used to help your body reconstitute and anabolize new bodily tissues. Vitamins are going to assist in all those processes, and minerals are also going to assist in that process in some cases, while giving your body structure in other cases. And water is what gives your lymph substance, and the same thing with your blood, right? There's a lot of water in your blood, there's a lot of water in your lymph, and that's what's moving everything around the body. So we'll start off by talking about digestion, because we can't do any of that unless we get it really small, right? Like we got to be able to get these materials from that outside environment to the inside environment. And if they're going to do that, they got to get real small. So that's where digestion comes in, right? It is the segregation of foods into basic units for absorption by the cells in the GI tract, right? So your gastrointestinal tract. So what we're taking food and we are breaking it down so small that it can actually pass through the walls of our body into our bloodstream. We are breaking food down into units that are so small that they can pass through the walls and membranes into our bloodstream. So we're getting it from the outside to the inside, right? So this is what that's going to look like, right? We've got our mouth, esophagus. That's going to be the beginning of your GI tract. It'll travel down into your stomach, where there's going to be a whole bunch of other materials like hydrochloric acid and pepsin and digestion and things like that. Then that's going to move into your small intestine, which is kind of tucked behind your large intestine here. And it'll kind of begin this little journey there. There's a little bit more breakdown that's going to occur there as well. You've got your liver, which is going to produce like things like bile, and you've got your pancreas, which is going to produce things like pancreatic amylase. And both of those things are going to share like a common duct where it will eject bile into your small intestine. Now, liver doesn't necessarily do that directly. It actually stores up some of that in your gallbladder, which is a much smaller little pear-shaped organ. So it'll store it in your gallbladder. but the bile gets made by your liver. And so all that gets ejected into that small intestine, and that's where everything finally gets really, 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 really broken down. And now, for the most part, you've got this wet, soupy mixture, right? And that wet, soupy mixture is full of just chemicals, right? They're not really, it's not really food at this point. It's just a series of different chemicals, and your body is going to absorb those chemicals using your small intestine. And once all that's been absorbed, all this surface area has allowed all that absorption to take place, it'll then make one sort of lap right around your large intestine, where a lot of your water and electrolytes are going to be absorbed. And finally, it'll make a nice exit out of the body, right? So let's go ahead and break down that gastrointestinal tract. Gastrointestinal tract or GI tract, right? So that's going to start at the stomach, which we just mentioned, right? Which is a pouch which receives foods from the esophagus, right? And there's going to be, it's filled with hydrochloric acid and other materials that break down food to chemically alter it into a wet, I don't want to say that actually, a mixture called chyme. Okay, so when it's that wet, soupy mixture, it's not really food anymore, right? Like, it's not really food, but it's also not really like poops either. It is chyme, right? Which is this kind of wet, soupy mixture. Not to get too gross, but it always happens whenever we're talking about the digestive tract. But if you've ever been really, really sick and everything has kind of come out the back end, that is basically, you're looking at chyme. Your body was like, okay, we're not absorbing any of that. That is compromised with bacteria or viruses or something, and we got to get it out of the body. So it didn't really take time to get absorbed. Your small intestine just kind of rushed it through to your large intestine. Large intestine was like, I don't want it, and then rushed it through, and then it made its exit, right? So what you are basically seeing is chyme. That is what you're going to see in your stomach there. And then you've got your small intestine, right? Which is going to be the next tract, which is a portion of the GI tract where maximum digestion and absorption occurs, right? So this is where really you are doing most of the absorbing when it comes to foods, right? So your small intestine, you're going to see performs a bit of digestion with enzymes that are created by the liver and pancreas and excreted into the first portion of the small intestine, right? Exerted. Nope. Oh, I said the twice too. Ooh, this sentence is a mess. So your body is going to sort of allow that bile and some pancreatic amylase and other enzymes, which are coming from those areas. So inside of that, right, you've got your liver, which is an accessory organ designed to create bile, which will emulsify fats. Right, so bile's job is to break down fats. You have got your pancreas, which will, an accessory organ, which will create enzymes to further break down carbohydrates and proteins, right? And then you also have your gallbladder, which doesn't make anything, but it gets all the glory for dropping off all that bile. A small pear-shaped organ that stores up the bile created by the liver and drops it into the small intestine. Okay, so there's all those accessory organs, right? Where there's still a little bit of digestion that's happening, right? Like your stomach's job is to really just chemically acidify stuff. But all of these little accessory organs really do all the final work of digestion there. And now, in that all happens in the first part of your small intestine, which is called the duodenum. And then it'll move to like the jejunum and the ileum, which are the jejunum is like the main body of the small intestine, and the ileum is right before it's about to become your large intestine. And so all of that is like the digestion part of your small intestine. And then finally, we are ready for absorption, right? And so it will also performs maximal absorption due to the massively increased surface area due to intestinal villi, right? So what are your villi, right? Villi are rod-shaped projections that cover the walls of the small intestine that act as the actual site of absorption by allowing chemicals to pass into the bloodstream. Okay, so if we look at like our villi, right? Villi, Billie Eilish, villi and microvilli. If you look at this here, you can see like this is like what the walls of your intestine look like. And you see these kind of like these, kind of big folds here, like the ring shape that you see. Those are called lumen. And then on each of those are all these little small projections, these little hairs. Those are your villi. And then in your villi are covered in blood vessels. And they are also covered with their own hairs called microvilli. And microvilli are in charge of like moving materials around so that they can actually get to the hole that they are supposed to fit through. One of the things that I always like to, we already talked a little bit about this when I talked about like artificial sweeteners with you guys, but your body has, specific shaped like channels and pumps and things like that that allow certain materials into your bloodstream, right? And it's only designed to, like, that's what makes something a nutrient. That's what makes something food, right? Carbohydrates, those can totally pass into your bloodstream. Proteins or amino acids, those can totally pass into your bloodstream. Fats, those can totally pass through. But like like your minerals and stuff, iron, magnesium, sodium, potassium, all those different types of rocks, those can all pass into your bloodstream. Now, things like, what's another metal that's not gold, right? Let's say you swallow a gold ring. Your body doesn't really have the materials necessary to be able to digest that type of material, right? Like it doesn't really have the tools in its tool belt to break those gold molecules down. But I mean, like, it's not to say that it's impossible to get it into your bloodstream. You still could. It just has to be broken down small enough that possibly it gets into your bloodstream somehow, right? Like if you were to get it like a very small microscopic version, a square can't fit through a round peg, right? Unless it's a really tiny square, like, that's kind of how we like to think of it. And that's how like, artificial sweeteners, they're not, your taste buds create like a chemical reaction because they bind to taste receptors, but for the most part, they're not foods. Your body's like, I don't know what that is, and it pees most of it out. It just passes most of it right along. But the small bits of it that do get into your bloodstream, your body doesn't have anything to do with it. Once it's in your bloodstream, it's in your body. Your body can't do anything with that material, right? It's not food. So what it'll do is it'll just kind of store it. It'll put a little bubble around it and store it in some tissue somewhere, probably fat tissue, and just kind of hold on to it forever. Just like viruses, right? Kind of funny. Oh gosh, Frankie. I think I'm getting a lot of reverb there. I can hear myself. That's what's kind of funny about like viruses and stuff, right? Like a lot of people think that like your immune system just destroys that virus and it goes away forever. That's not 100% true. Like your body holds on to that virus forever because it's in your body, a living organism. Hey Frankie, can you slap the mute button? uh, it's this like living organism that your body like destroyed, and then it keeps all the pieces of. And that's why, like, remember when you were a kid, your parent and you got like the, anybody's parents do this. If you got if your cousin or something had the chicken pox, and they were like, oh man, let's get my kid the chicken pox so they can get over it, because it's easy. It's much more pleasant when you're a younger kid, right? My parents totally did that. My cousin got chicken pox, and then like my mom heard about it, and we're like, well, we're setting up a play day, and she like drove me down to hang out with my cousins, and they did everything in their power to make me catch this freaking virus. And so like sure enough, like I caught it, and I remember like being all itchy and stuff. The thing is, like, that virus wasn't destroyed by my immune system. Like I got over it. Like my immune system fought it off, and I'm good, right? But it's still dormant in my body forever. And that's why, like, as an adult, you can get what's called shingles. And shingles is like a much harsher version of the chickenpox virus that remanifests itself. So your body never gets rid of anything. Remember when we were talking just the other day about like the first law of thermodynamics, right? Anything that's like created, exists. You can't create or destroy anything. You can just make it change from one form to another. Once it's in your body, it's in your body. That's true of those artificial sweeteners. That's true of everything. So we kind of need to be aware of that, right? We need to kind of have that awareness when we start to consider. I was like, well, why would artificial sweeteners be bad for us? Well, it's something that's not food in your body, and now you have a clump of cells that are covering it up. Now your body's not really designed to absorb it, but it still can. And we're going to kind of come back to this concept in a little bit, but I wanted to use that to kind of highlight like how absorption actually works, right? You are designed to be able to absorb certain materials, and you're not designed to absorb other materials. And that's kind of what keeps some things in and some things out. If you've ever, your dog and your cat, they totally work the same way, right? Like any animal has like a digestive system. It all works basically the same way. But if you've ever had your dog, so you left something on the counter and they ate like a candy wrapper, and then like sure enough, a couple hours later on the lawn, you got to pick that out, and it looks kind of the same as it did a few hours ago, just a little covered up, like the ink's the same, the plastic's the same, it all looks the way it did before. The reason that didn't get broken down is because your digestive system's not designed to break that down, right? That's what makes something a food or not. And so anyway, I always love to mention that, because like we have to understand that in order to understand like what absorption actually is. So your villi are the sites that have the specific size slots to allow for food to pass into your bloodstream, not other materials. Now you do also have your large intestine. And your large intestine is the terminal, the last portion of the GI tract that collects undigested, semi-digested foods or unabsorbed contents. So if something wasn't food, so for instance, you have things like fiber in your diet, right? Fiber is primarily made of cellulose, which unfortunately our digestive system just doesn't have an enzyme powerful enough to break down. Cellulose is a form of carbohydrate, but it's stacked together so efficiently in the cell walls of plants that our bodies can't really get to it. Our body can't cleave off the glucose molecules. And so, they're stacked so efficiently, your body doesn't digest them, which is a good thing, because then it actually travels through a digestive tract and gets to the large intestine, and the large intestine is able to kind of clump it all together. And then any other materials that your body couldn't digest gets wrapped up in all that fiber and pushed out of your body. So we are really thankful for the fact that we can't break down, certain materials. And your large intestine is going to, be in charge primarily of like defecation and stuff. But we got to be aware it also is in charge of like absorbs the final parts of water into the bloodstream. So that's a really big important thing, right? Our body is absorbing nutrients, one of the most important nutrients, which is water, in the large intestine. And it also absorbs any remaining electrolytes via the water. So remember, electrolytes are primarily things like sodium and potassium, right? And it's really important that you get those into your bloodstream so that your body can use those to generate action potentials. Well, a lot of those are actually absorbed via water. They're carried very efficiently by water. And so a lot of that does get absorbed in your large intestine. So it does play a very important role in keeping us healthy, and that's why you want to have, and there is a small accessory organ there as well, I guess I should mention. Your large intestine is going to connect to your appendix, which is going to be an accessory organ that we think is responsible for housing bacterial cultures that assist in digestion. Okay, so with any final digestion that does take place in the large intestine is because of all of your gut bacteria. So one of the reasons why it's so healthy to eat, fermented foods like kombucha and yogurt and kimchi and stuff like that. The reason that stuff is considered so healthy is because you're eating a large amount of like bacteria, and that bacteria can actually assist in breaking down foods. I know a lot of times we think of like bacteria as the bad guys, but bacteria is actually a very good thing, and it's actually very small too. Here's a weird fun fact for you. You have more bacteria in your body than you have human cells, because they're way, way smaller. So there's a weird, bar trivia fact for you. Let's go ahead and take a look at our nutrients here. So we've talked about like how we absorb nutrients. Let's talk about what those nutrients are, right? So we're going to go a little bit more in depth here, which is funny because we're about to go super in depth over the next couple of days. But carbohydrates, right? Carbohydrates are made up of simple sugars. So we have to classify, actually, you know what? Let's go. Let's go like that. No, what? Hey. Oh my God, freaking thing. All right, fine. We'll do it like that. All right, so essential nutrients. These are like those nutrients that you must consume, right? So we're talking about carbohydrates here. They're made up of simple sugars, right? They're big complex chains of sugars. So we need to have like kind of a labeling system for what we're talking about when we talk about like what types of carbohydrates you're going to be consuming. So you have what are called monosaccharides. Monosaccharides, which are single sugar molecules, right? Glucose is a really good example of this, right? This is actually what we use to produce metabolism, right? We need those single sugar molecules. So that's as simple as it gets. If you have like a bunch of glucose, your body has done its digestive job. But you do also have disaccharides, which you'll get in food sometimes, which are double sugar molecules. Actually, we'll put it the way we got it here. Consist of two linked monosaccharides. Right, so this is two sugar molecules linked together. That's a disaccharide, right? You're going to find that in things like fruits, for instance. And then we've got oligosaccharides, which I'm actually going to skip. Oligosaccharides is not really that important of a term. I mean, it's kind of an important term, but it's not that important of a term. Oligosaccharides is like 3 to 10. But what most people say is they just kind of disregard that oligosaccharides exist, and they just call it a polysaccharide at that point. If you have 3 or more, it means many. And so we're just going to call that a polysaccharide. That's even how it's presented in your regular NASM textbook. So I'm going to go ahead and list that version of this out here, actually. So then you've got polysaccharides, which are many sugar molecules linked together. Okay, so there's going to be a couple different versions here, right, of polysaccharides. These are going to be things like starches, glycogen, and fiber, right? Which is like fiber is like a super polysaccharide. Like that's a super complex one, like we just talked about, right? So those are those essential nutrients there. Now, kind of going back to like the enzymes that assist breaking down carbohydrates. Carbohydrates are, carbohydrates are easily broken down by the digestive system thanks to a series of enzymes. So the primary one that we generally talk most about is what we call salivary amylase, okay? And so salivary amylase is a digestive enzyme in our saliva that converts complex carbohydrates into simpler sugars, right? So salivary amylase is going to split polysaccharides into disaccharides, right? So it can't break it all the way down. Unfortunately, salivary amylase is not powerful enough to get all the way down into glucose, but it is able to get it into double sugar molecules. And that's why, like, if you chew like a piece of bread for a really long time, you'll notice it will actually start to taste sweet. And that's because you are digesting that bread in your spit and doing something that's kind of weird. Now, we do also have pancreatic amylase. Not saying you shouldn't chew your food, but this is the enzyme that is secreted by the pancreas and assists in the digestion of starches. So if you have like a big complex starch that's, doesn't really get effectively broken down by salivary amylase, pancreatic amylase is much better at breaking that down inside of your digestive system. So that's where that's going to be created by your pancreas. That's dropped off, at where the stomach and the small intestine meet there. So what do I mean when I'm talking about like a starch? Well, starch is the storage form of carbohydrates in plants, right? And it's big, long chains of glucose molecules all held together. It's a classic example of like a polysaccharide, right? It's many sugar molecules. Now, you have special, like your own special version of starch, which we're going to call glycogen. And glycogen is like our version of starch that we store. So like in the same way that plants store carbohydrates for energy, we store carbohydrates for energy as well. Plants do it in the form of like a lot of different types of starches. Like I can't remember, unfortunately, I can't even remember one right now, which is weird. Types of starches. No, I want the chemicals. There we go. So these are a couple different types of starches that you'll find in like certain vegetables, right? So you're going to see like amylose is one, amylopectin is another. These are just different things that you're going to find in like different types of foods, right? Amylose, I think, is found in like potatoes. I think like amylopectin is found in more like sweeter vegetables and things like that, probably like peas. So there's a bunch of different like types of starches, and that's where those like oligosaccharides sometimes come in. Like when you think of corn, right? Corn is a little sweeter than like a potato is, right? But then you have like sweet potatoes, which are, definitely sweeter than like, whole wheat, you know? So like there's different like types of starches and different types of oligosaccharides. We're just going to call all of them starch as kind of a blanket term because we don't really need to know the difference between them. Our digestive system treats them all the same. It breaks them into glucose. So it doesn't really matter what type of starch they are. Now, if you're a chef, it totally matters, right? It's like really important. And this is why like you boil some potatoes for 20 minutes, and I don't know if that's true. And you boil other potatoes for like less time, you know, like there's different like times and like ways that you do things and like when to add, if you're making mashed potatoes, like when to add cream, that goes at a different time. Like, you know, russet potatoes make a really good mashed potato, but red potatoes make really good roasted potatoes, you know? The reason for that is because of the different types of starches and the different types of like saccharides that they have inside of them. And we are officially at the end of my cooking knowledge. I got the chemistry, and now we're stuck. So that's what amylase does. Now, you do also have one other thing, which are called your brush border disaccharides. These are really cool, actually. Brush border disaccharides are actually digestive enzymes produced by the cells in by the cell walls of your small intestine, and they break disaccharides into simple sugars. So let's say you don't get something all the way broken down, right? Let's say it somehow survives all the way to your small intestine. Well, you have these brush border disaccharides, which are activated literally by brushing the wall, like brushing the border of your small intestine, and they've actually got some enzymes there. They're like, how did you survive digestion? And then they break it down. And that's what your brush border disaccharides do. They're kind of their own unique types of enzymes. So there we go. There's all the different types of enzymes that kind of break down carbohydrates. Now, how the heck do you actually absorb all of these nutrients, right? I forgot this goes in like a really weird order here. So you're going to do this through a series of different types of like, you know, diffusion, right? So like, not to do like a whole big long talk on diffusion, but basically diffusion is the movement of like molecules in the direction of like a concentration gradient. So, you know, for instance, like even if you were just like pour out like a glass of water and it were to travel that way, that water is diffusing that way, right? It's traveling in the easiest direction possible. That's basically what diffusion is. So if you have a lot of stuff over here and very little stuff over here, it's going to naturally move in that direction. That's diffusion. Now you also have facilitated, that's passive diffusion, it moves naturally. Facilitated diffusion is kind of different. Facilitated diffusion is like, let's say you have like a protein or something, or maybe even just like a muscular contraction, and that pushes something in a direction. That's still moving in a specific direction, so that's still diffusion. But usually you have like carrier molecules that allow this to happen. So for instance, like remember how we have fat-soluble vitamins and water-soluble vitamins, right? Well, fat-soluble vitamins use facilitated diffusion by like those vitamins attach themselves to a fat molecule in order to be carried in a certain direction. And the same thing is true of water-soluble vitamins. They attach themselves to water molecules to be carried in a specific direction. You also have active transport. Active transport is really cool, actually. It's kind of like shuttles, where your body will like have a little protein, and that protein will kind of fly up and grab something, and then like work its way to the other side of something and drop it off. And then you have my favorite version, which is called endocytosis. And endocytosis is one of the coolest things that your body does. Endocytosis comes from the word, if I'm not mistaken, it stands for devouring cell action. And that's literally what it is. What endocytosis is basically like a material will be like over here, and then like your cell will kind of like shimmy up to it, and then just like fold itself over top, and then it'll enclose the whole thing, and then it'll open up its inner membrane, and now suddenly that thing is trapped inside, and then it starts to get dissolved. That's how your immune system actually kills viruses. Your immune system basically eats them. There's one more, by the way, but it doesn't have anything to do with like absorption of nutrients. But another way that your immune system works that I also think is really cool is called pinocytosis, which is drinking cell action, and that's actually before that material gets like eaten by your immune system. Your body will mark it for destruction. So what it'll do through pinocytosis is it'll kind of like shimmy its way over, and then it will stab a virus. It'll create like a little projection from the cell, and it'll stab it, and then it like either injects it with a protein that then the rest of your digestive system comes and eats it, or it'll straight up drink it all and dehydrate it, and then it'll die. Your immune system is brutal. And I actually really enjoyed talking about it, but we're moving on. So in endocytosis, your cell walls open up, grab materials, and bring them in. So that's how stuff, when I mentioned that stuff is moving into your bloodstream, most of that is happening through passive diffusion. That's the most common way. You got empty holes, and things that are small enough can go through those holes and get into your bloodstream. But certain materials need to have like active transport. Vitamins and minerals, for instance, they can't get in there without, because like fat, the membrane around the outside of your walls are keeping them on the outside. So fat can allow that to pass through, or maybe like a protein channel that allows water to pass through can allow it to get in that way. So you do have to have specific ways to get stuff in. So now that it's all in your blood, you have what is called a hepatic portal system. And what that means is once it's in your bloodstream, the first place that food is going to go is through your liver. Okay, so the hepatic portal system is going to collect all those nutrients from your small intestine, and it's going to shoot them straight up to the liver for detoxification. So if you've ever heard of like how your liver detoxifies things, this is what it does. And if you've ever heard of something like cirrhosis, right? Cirrhosis of the liver is basically your liver's not working anymore. That's what usually happens due to like overconsumption of alcohol or certain drugs or things like that, right? Your liver is like, I don't know, that does not help me produce metabolism. I'm going to detoxify the crap out of it. And if you just do that all the time, it gets overwhelmed and it starts to destroy those cells. Luckily, your body's also able to kind of bring them back. Your liver is one of the hardest to kill organs inside of your entire body. If you were to, I don't know why you would do this, but if you were to like cut it in half, actually, it would mostly grow back, which is kind of cool. Your liver is awesome and super hard to kill. But doesn't mean you should try. Somebody tell that to my parents. All right, so your hepatic portal system is going to bring everything in. Now, once materials are brought into your body, like I said, they're going to go straight through your liver, and your liver is going to store some of those carbohydrates. So carbohydrates and all other nutrients will pass through the liver once they are absorbed. Okay, and then in your liver, the liver will store excess glucose in the form of glycogen. Okay, so glycogen is basically our version of a starch. It's kind of like pectin, like I talked about earlier, and all that amylose and stuff like that, the starchy stuff in potatoes. In fact, whenever you are boiling like a pot of potatoes and you see some of that scum kind of seep to the top, that's kind of what glycogen actually looks like. It's this kind of wet, soupy mixture. And we have it in our muscles. This is actually why, has anybody in here ever been hunting? Like deer hunting or anything like that? So if you ever go, like, there's kind of a rule. You think that like you take out an animal and then you're like, yeah, let's eat that now. It's super fresh. It's actually not a great idea. You actually want to wait a little while because that animal's muscle had all of this stored glycogen in all of its muscle fibers, and it hasn't really broken down yet, and it tastes super, super bitter and is not a very pleasant sensation, or so I am told. Definitely not something that I've actually experienced. But that's kind of like, you know, that's how glycogen is stored. Most of it is going to be found in our liver, but it will also be stored throughout your muscles as well. So excess glucose will be stored in the form of glycogen. Glycogen is the storage form of glucose in the body, right? It is a polysaccharide. So it is a big complex sugar, right? Just like any other, or starch, right? You can think of it, it's a starch. Now, one thing that your body will also produce is insulin in response to those carbohydrates, right? So insulin is a hormone that's going to be created by your pancreas again, and that's going to help lower those blood sugar levels, right? So insulin is going to allow your body to pull that sugar out of your blood. So now think about like all that carbohydrates that like running through your blood, right? It's running through your entire system, taking up space, right? Like essentially it is. It's taking up space to carry oxygen and other materials, right? Because now you're carrying all this sugar that you have officially broken down with your digestive system. So now sugar passes in, goes to your liver. So my liver's way over here. Some of your liver is going to grab some of that and store it as glycogen, but the rest of it's then going to travel throughout your entire body. Well, in order to use that sugar, you have to have insulin. And insulin is a hormone that is going to lower your blood sugar levels by triggering the conversion of glucose into something, right? Now, that could be glycogen, or it could also be fat. And so you do have these specialized glucose transporters, your GLUT1 and your GLUT4. And what they do is GLUT1 carries glucose molecules into your muscle cells when your insulin levels are low, right? That can allow your body to produce that for energy. And then your GLUT4 is going to transport glucose when your glucose insulin levels are high. So let's say you have like a lot of insulin and your muscles are like, yeah, we don't really need any more glycogen. We're good here, you know? Your body can use GLUT4 to trigger pulling that sugar out of your blood and instead convert it into fat, right? Which kind of brings us next to our next nutrient here. Where the heck are nutrients? They're on the white. Okay. So this is going to lead us to lipids or fats, right? Which are going to be complex, made up of fatty acids. Okay, so you get a couple different versions of fats here, right? You've got straight up lipids, which are, what we actually call like a fat, right? So a lipid is composed of a glycerol molecule with 3 fatty acids attached to it. That's the one that we call a triglyceride, right? So of your lipids, you are going to have triglycerides, right? Which are glycerol molecule and 3 fatty acids attached to it, right? So that's what a triglyceride is. Then you're also going to have a diglyceride, which is more commonly referred to as a phospholipid. It is a glycerol molecule and 2 fatty acids attached to it, right? So this is actually what makes up your cell wall. So if we look at our phospholipid bilayer, if you look at like the cell wall here, you can see it's made up, like there's our phospholipid, right? That's a glycerol here, and then there's the 2 fatty acids, and you can see it's 2 layers here. And so what this does is you've got a what is called hydrophobic end. That means that it's afraid of water on the inside here, right? So the little tail sides, like fats and water don't mix, right? One of the reasons why if you ever pour oil into water, you'll notice it'll clump up into these big balls. And that's because fat automatically kind of arranges itself in this position here. And what it does is it faces the side that's afraid of water inward, and it faces the side that likes water, which is your hydrophilic end, outwards. And that keeps water over there and keeps fat over there. That can have them easily separated. So whenever you're looking at water in like a, or oil in water, if you've ever poured that in there, you are actually seeing this arrangement here, which is the same arrangement that keeps fluid, like makes up every single solitary one of your cell walls. This arrangement right here is what keeps, your cell walls to having their shape. Now, they will be straddled by things like this, like little proteins and channels, and that allows materials to pass through them. So that outside environment that I was talking about earlier in your digestive system, the way that we keep it separated is because of like your cell walls. So that is going to be a diglyceride or a phospholipid, right? And then you are also going to have like monoglycerides. Oops. Which is a glycerol molecule with one fatty acid attached. Okay, so if we look at like a monoglyceride, right, that's a single, very uncomplicated fatty acid, right? This is about as simple as it gets, but it does still have like that glycerol molecule there, right? So you're gonna find these things in like super complicated fatty acids, right? And because those are so simple, they tend to be very undense. And because they're so very undense, you are going to find them in a lot of oils and baked goods and trans fats, actually, which are going to attack your other fats, right? They don't have enough density of their own, so they actually kind of attack all those good fats that we've been talking about until now. And then lastly, we don't have a glycerol molecule anymore. We just have the fatty acid. Instead, if we have that all by itself, we have what is called a free fatty acid. And that is a fatty acid that has been cut from a triglyceride molecule and can be used directly for aerobic metabolism. So what's cool about free fatty acids is that can now go through, that can actually go through normal metabolism. So you have like a triglyceride, and it's got 3 little bits that it can break off to go through metabolism like we're talking about. And that's why your body actually stores triglycerides, right? So triglycerides are going to be stored in your fat cells. They're stored in your adipocytes. Now, if you take a look here, there are a couple different places where fat is digested, right? Some of it is taking place in your mouth. That's in the form of like your lipase, right? Which is similar to salivary amylase. This is why fat tastes so good. That's also why sugars taste so good, by the way, which is why our food is, full of them. Some of it will also happen in your stomach, right? You've got lipase in there as well. But primarily, most of it is thanks to like bile and pancreatic lipase, right? Both things which are going to be found in your small intestine. So triglycerides and diglycerides are going to be broken into free fatty acids, monoglycerides, and things like that so that your body can actually use them. So types of lipase that you've got: lingual lipase, right? That's on your tongue. Gastric lipase, that's in your stomach. I hate this one. Cholecystokinin, that's what it is. I can never say it. But that's, actually a hormone that releases pancreatic enzymes. Secretin, the same thing. You don't necessarily need to know those, or pancreatic lipase here. But those are basically all the enzymes that are allowing this breakdown to happen. Now, there are a few other things that you are going to find inside of when we are talking about fats, and one of those is going to be lipoproteins. Okay, so lipoproteins are substances that transport lipids in your lymphatic fluids and in your blood. Okay, and what a lipoprotein is it's a regular triglyceride, but it has a protein shell made up of like some phospholipids and cholesterol. So if we look at like a lipoprotein, there we go. This is what a lipoprotein actually kind of looks like, right? This is a big, super complicated one right here, which I can never say properly. Chylomicron. But that is your classic big lipoprotein right there. So you can kind of see there's some proteins here, you've got triglycerides in here, and then there are little cholesterol molecules in here as well. Now, you will also see two types that we are primarily familiar with, which are LDL cholesterol and HDL cholesterol, okay? So LDL cholesterol is your low density cholesterol, which means you can see it doesn't have very much glycerol in it. It's only filled with cholesterol. Also on the outside, you can see there's a lot of fatty acids making up its cell wall. Whereas HDL cholesterol, which is your high density stuff, it's more tightly compact. You're going to see more triglycerol, and you're going to see less cholesterol molecules in here. And that's why this is considered your good cholesterol, and this is considered your bad cholesterol. And this is part of your total cholesterol. You don't have to worry about this. But these guys right here, these are kind of the two key players here. So when we talk about like what a lipoprotein is, right? Lipoproteins are substances that transport lipids in the blood, okay? Consisting of lipids, cholesterols, and proteins, okay? So you have special proteins that you are going to find in fats. Now, those good cholesterols, right? You do have to be able to kind of break that down, and luckily you have an enzyme that does that. And this is sort of how that process is working. Don't worry about that. That goes way deeper than we really need to talk about. But talking about your lipoproteins, the things I do need to mention, you have low density lipoproteins, which is going to be cholesterol molecules, or actually I should say lipoproteins that are very high in cholesterol and low in fat. This is typically, this is the bad cholesterol, right? Think of it this way. This is your LDL cholesterol, right? Think of it as lazy density, right? This is the type of cholesterol that often parks itself on your blood vessels rather than continuing to move through your body. And that's not super awesome. So low density lipoproteins, they block your cell walls, they create hypertension, they cause all kinds of different problems inside the body. Then you also have your high density cholesterol, or HDL, right? That is going to be lipoproteins that are dense in fat and low in cholesterol. Okay, this is typically thought of as the good stuff. Can we not? Okay, that's the good stuff, right? You want to make sure that you're getting plenty of like good cholesterol in your diet. And so this is where, the debate about eggs has happened over and over and over again. It's like eggs are good for you, eggs are bad for you. Eggs are high in cholesterol, but we find they're really high in cholecystyrene, which I just can't say that word. And they're really high in like high density cholesterol, but they do also have substantial levels of low cholesterol as well. So really they're just high on all types of cholesterol. As long as you have like a balanced diet, eggs are fine. You don't have anything to worry about. They kind of cancel each other out with being full of good and being full of bad, but it will raise your total cholesterol levels. So if you're on like a medication, that results in your body like storing more of those lipoproteins, maybe stay away from eggs. All right, last macronutrient that we've got here, we've got protein, the one everybody wants to talk about, right? These are complex chains of amino acids, right? So you can have proteins in so many different forms, right? Those amino acids can basically change their order. and that's going to result in a totally different type of protein. Okay, so when your body is breaking these down, they're going to go through a process called denaturation, or they're going to denature those proteins, right? And it's the process in which proteins lose their interesting shape thanks to enzymes. So when you look at like a protein, I don't know if I'm even going to get a really cool picture here. Yeah, there we go. I'm just getting different types of proteins here. I love it. These are kind of what proteins look like. They're able to kind of fold themselves in these really interesting shapes. You know, you'll see plates like this. You'll see swirls like that, squiggles like this. This actually, I'm pretty sure this is a hemoglobin molecule. You'll see like an interesting structure with like around the outside with like a framework on the inside. You know, there's a lot of different types of proteins out there. And then there's the classic, I can't believe they're not showing the most famous one. Holy crap, look at that. Where's the double helix? There we go. There's the most famous protein. That's your DNA, right? And it's this interesting like protein on one side. I guess it's all the swirls that kind of counts, but wasn't seeing, you know, this specific framework here. So, you know, your proteins obviously a very big part of like what make up us, right? They are these kind of big complex chains here. When you go through the process of denaturing protein, it basically loses its really cool shape and gets broken down into really simple versions, okay? Now you are gonna have some other enzymes in there as well, things like proteases and peptidases, and those are gonna help break down those amino acid bonds. But this is what's happening when you denature a protein. It doesn't have to be enzymes, by the way. You can also do this by superheating things. Here's a fun question. Let's see what you guys think here. Does anybody think that microwaves reduce the nutritional value of your food? Raise your hand. Raise your hand. Say something. Oh my God, I just reverted back to being in normal class. Yeah, so it could, theoretically, it could reduce the nutritional value. Now, for the record, there's nothing dangerous about microwaves. Like what a microwave is it's a machine that makes a bunch of microwaves. Thanks for that, science. But that's what a microwave is, right? Your microwave oven is this little thing that creates these little like tiny waves, and when those waves interact with water, it makes them bounce a whole bunch, and that causes a bunch of friction, which causes food to heat up. And that's cool, right? It's a type of radiation that's not really all that dangerous. Now, does it reduce the nutritional value of your food? Maybe. So in order to understand this, we're going to kind of pivot to a different topic. Let's say you're cooking a chicken breast, and you're like me. I used to do this when I was younger all the time when I first started cooking. You forget that you're cooking. You know, maybe you put it on there, put it on low heat or medium heat or whatever, and then you're like, oh, no video games. And you walk away. And you forget. And then all of a sudden your smoke alarm's going off and you're like, oh crap, I was cooking. And it would burn your freaking house down. And now you have this charred, blackened, nasty chunk of what used to be food, right? So what you did is you just denatured the heck out of that protein. You are left with a bunch of like burnt up carbon. Because proteins do have carbon in them, right? Just like carbohydrates do. You have basically destroyed all those proteins, and now all you can really see is the carbon. That's also why, you know, your food shrinks so much. You know, all the water's been dehydrated, and your body just squeezed it all, or I'm sorry, the heat just kind of squeezed it all together and denatured the crap out of it. The nutritional value of that protein has definitely dropped significantly. Now, you can do that in a microwave very, very, very easily. And the food doesn't end up looking all that different. But you still overheated it and did destroy some of that nutritional value. But microwaves inherently don't destroy the nutritional value of food. Over microwaving something does. And it's very easy to over microwave something. I mean, I've done that a million times where you're like, oh, the center of this is freezing cold, but the outside is going to burn me, burn me alive. Well, the outside lost some of its nutritional value, and the inside is pretty much the same as it was. So there is actually like evidence to suggest that microwaves can damage your food, but you have to like over microwave something in order for that to happen. And because microwaves are kind of touchy, that happens to be easy to do. Me personally, I microwave literally every meal I eat every single day. Because I make all my food on Sunday and then I just heat it up throughout the week. And am I losing nutritional value? Maybe sometimes, you know, maybe I am every now and then if I overdo it. But, you know, it's better to err on the side of like slightly cooler than it is on the side of like slightly hotter in the realm of like maintaining nutritional value. Although obviously with doing that comes the risk of like bacteria. So pick your battles. That was a classic nutrition talk right there where it's like, well, what should I do? Your choice. All right, but I gave you the information. All right, so here's how proteins look, right? You can kind of see these big complex chains, right? These are all the amino acids here. And your body is going to cleave off different sections until you're left, you know, with individual amino acids, right? So what is an amino acid? Once again, right, is a complex chain of carbon, hydrogen, oxygen, and a special skeleton of nitrogen, okay? And nitrogen is really the key player here. Nitrogen will shape itself very differently in each amino acid, giving us the 20 amino acids, okay? Now, in the process of digestion, what ends up happening is your amino acids get broken down into what is called your amino acid pool. Your amino acid pool is a collection of amino acids found in the body fluids and tissues that allow for protein synthesis. Right? So, for instance, your liver can actually store a whole bunch of amino acids inside of it. And so when your body is like, hey, liver, we cut our big toe by stubbing it on the door today, you know? And then your skin, and so your skin's like, I need more skin cells down here at the left big toe. And so your amino acid pool is like, great, cool. And so it travels from the liver through your blood, gets down there, and then your body starts assembling those proteins into new skin cells. And that's what another job of your immune system is. Now let's use an example that we actually use in the world of training. So let's say you do like a super heavy leg day. Like I am feeling it like crazy today. So let's say you did a super really hard leg day and you tore your leg muscles up. You have this inflammatory response by your immune system. That's what's drawing amino acids and other materials to that part of your body so that it will result in new tissue being built up to repair all that damage that you created with these specialized cells called cytokines. And cytokines are really, really cool. Now, your body can, if it needs to, oh, and hold on, I gotta really quickly talk about DNA here. We're gonna keep this short. DNA is not really all that direct in our field, but DNA is basically a specific type of like protein, right? And so the way your body does that is it reassembles those proteins to make up like new DNA molecules. And when your cells split, your body will create what's called RNA, and RNA is basically like half of a DNA strand, and then what that'll do is that'll trigger the creation of the other half to reconstitute it, and bada bing, bada boom, you got a new cell. And that's really cool. That whole process is called transcription, which I love that we named it that, because it's literally like, you know, it's like if you were reading something in French and you were turning it in English. That's kind of what RNA is. It's like you got an RNA molecule and you're like, what, how do I make this protein? Okay, great. And that's transcription. All right, that's all of our macronutrients. Do you guys have any questions so far? Am I moving too quick? No? Awesome. All right. Okay, let's look at our minerals, vitamins, and waters here. So minerals Actually, am I going to get minerals first? What am I getting first? Vitamins, of course I am. It always goes that order. It always goes vitamins first. I don't know why. It's just like an unwritten rule. It rolls off the tongue better. Vitamins and minerals. Absorption doesn't need to necessarily break down these things, right? Like for the most part, like vitamins and minerals don't get broken down by the body. That's not really their job, but they do need to get absorbed by the body. And so the vitamins and minerals that are found in food need to be carried by either fat or water in order to be able to get into the actual bloodstream. And that's where you do have your two types of vitamins, right? So vitamins are, these materials similar to proteins actually, but materials that are responsible for aiding in certain metabolic processes, right? Now, like I said, you have your water-soluble vitamins, which we'll do more talks on all this in a few days here. But water-soluble vitamins are vitamins that dissolve in a watery mix and are absorbed along with water. So the vitamins here are going to be your B vitamins and vitamin C. That is the list of water-soluble vitamins, okay? So those are in charge, right? Remember, B vitamins are the ones that act as coenzymes, right? B vitamins, coenzymes, right? If you look at like the Krebs cycle, right? B vitamins are actually assisting in that entire process, right? That's how you're getting a whole bunch of that NAD and FAD is because of all those B vitamins. They're kind of kicking this off. So biotin, folic acid, niacin, all of those are B vitamins. And that's another thing that sometimes like freaks people out when you start talking about nutrition. Sometimes they'll say, hey, this is vitamin B8. And sometimes they'll say, hey, this is folic acid. I'm not sure that's the right number for that type of vitamin. I used to know that because I had to pass the test. You'll want to know that at some point. Is it helpful at all? No. The one I got memorized is B6, and that's your riboflavin. That's the one, by the way. You ever take like an actual like vitamin supplement, right? Let's look at a men's multivitamin here. Rainbow Light, sure. I saw it. There we go. I don't know what that is. This is not an advertisement. Okay, that's how is that at all helpful? This one's better. There we go. All right, take a look here. If you look at like riboflavin, it has 25 milligrams in it, and that is 1,471% of the recommended daily intake. 1,400%. That is a lot. So why the heck? And we know that too much of certain vitamins can actually make us sick. They can, halt certain physiologic processes. They can be dangerous. So why the heck are we allowed to take 1,400%? Well, it's a B vitamin and it's carried by water. So you know what your body does when you get too much of it? It just pees it out. It just runs it through your water and it comes out the other end, which is why everybody in here has probably taken a B vitamin at some point in their life. Well, I'm sorry, if we've taken a multivitamin at some point and, you go to the bathroom later and it looks like the Hulk's pee. It's like so bright yellow, it looks like it's almost fluorescent green. It's like you're peeing a highlighter. That is because there is just extra riboflavin. Your body's like, I don't need any of this. And it's just sending it straight through your body. It's nothing to be alarmed at. It's nothing to be like afraid of. But that's what a water-soluble vitamin is. We can give you massive amounts of water-soluble vitamins and not be too worried about it. But fat-soluble vitamins, they're absorbed in fat, and you got a lot of fat throughout your entire body. So that's the stuff that it can actually be kind of a little more dangerous, but is also incredibly important. So let's talk about it, right? So fat-soluble vitamins. right, are vitamins that dissolve in fatty portions of the GI tract. Okay, these are vitamins A, D, E, and K. Okay, those are all of your fat-soluble vitamins. You will want to know those. I definitely recommend being familiar with which ones are fat soluble and which ones are water soluble, and then having a basic knowledge of you know, what each of them do. But for the most part, like, you know, having them memorize, like memorizing all of the B vitamins and like what number specifically corresponds to each one, not super important. A lot of the B vitamins, they all kind of honestly do pretty darn similar things. They are there to aid in metabolism. Vitamin C we know is related to immune function. Vitamin A is related to like eyesight. Vitamin D is related to calcium absorption. Vitamin E and vitamin K both act as antioxidants to protect the body against those artificial sweeteners that I talked about earlier. So they are all actually quite important, but you know, having a basic knowledge of like how to get those things in your diet and having a healthy, balanced diet is honestly more important than knowing all that like miniature technical stuff. So energy metabolism, obviously a big important part of nutrition, right? We cannot produce metabolism without all of this stuff that we've been talking about until now. And so first we got to kind of memorize, label out the largest version here. We're gonna, hold on one second, I gotta check to see, are we doing minerals? Fair enough. All of this stuff is related to energy. Minerals don't really do much in the world of energy, which is why I guess they're not really being mentioned here, but in for a penny, in for a pound. Let's really quickly do minerals. Minerals are inorganic substances that either make up body tissues or aid in certain physiologic processes, right? So the most common version of this are going to be electrolytes, such as sodium and potassium, aid in the body's, oh my God, typing ability to generate action potentials, right? Ooh, hold on. I had to squish a spider. Come here. Okay. So those are your electrolytes. All right, so those are, and those are, you know, an example of a different type of mineral. Magnesium, sodium, potassium, those are the classics. Okay, let's look at energy, right? Let's look at actually like doing stuff, doing work, right? So we got to talk a little bit about like our energy metabolism. So we've finally gotten to, and check this out, I think this may be a record for our note taking. We have finally made it to the second main bullet point of the day. All right, so energy metabolism, right? Is going to be how the body generates energy in order to do work, okay? So when we talk about like what metabolism is, right? We're talking about metabolism in a little bit of a different way today, by the way. Like in the past, we've talked about metabolism from the viewpoint of like, you know, direct ATP production and stuff like that. And we are going to talk about that right here. But today, we're talking about like the work part of metabolism, right? Like, does squats burn more energy, or do lunges burn more energy, or do push-ups burn more energy, right? We got to kind of look at all those things. It's going to depend on what you are good at, how much like you are going to actually burn during each of those different actions, right? So we got a couple different ways that we label how energy actually works in the body, right? So really quickly, metabolism. In the past, we've said it's any and all chemical reactions in the body. That is still true, but another definition for it is the total energy required to power cellular processes and activities, right? So we do have like a sort of a different definition here, right? It's the total amount of energy required. So we need to be able to break down like how we label metabolism in sort of two key ways here. So do you have a fast metabolism or do you have a slow metabolism? Well, that's going to be dependent on how many calories you are burning, right? So we're going to slap a number on it. If it's a high number, you got a fast metabolism. If it's a low number, you got a slow metabolism, right? You know, but that's all very subjective to you, you know? Like I can say with simple confidence, you know, and this, you know, is just how it works. The guys on this call right now, we have faster metabolisms than the ladies do, right? There's just more type 2 muscle fibers, which burn more calories. Generally, men tend to be a little bit taller and more like dense in the bone, right? All of that stuff just takes more energy, right? Muscle mass burns more energy than fat mass, right? But don't, you know, don't be upset. You guys get to live longer. So there are, you know, a lot of different like things that go into this. Let's go and understand what those numbers are, okay? So the first one that we're going to look at is what's called your basal metabolic rate. We're going to characterize this as your BMR. That's going to be the most common term you hear. By the way, just really quick so everybody remembers this, it has absolutely nothing to do with your BMI. It just sounds kind of similar. That is a common misconception that your clients will make, so get used to saying that sentence for the rest of your careers. Your basal metabolic rate is the minimum amount of energy required to sustain life in an active state. That bit right there is very important, right? So this is the minimum amount of energy that you require in order to live in an active state. Now we also have your RMR, that's your resting metabolic rate, or RMR. That is the minimum amount of energy required by the body at rest. Okay, so, oh, my mouse, stop it. So if I were to conk you on the head and you were to go into a coma and you were just stuck there, you know, not being active and just kind of sitting around, right? That would very much be your RMR. Just about 8. I was trying to stand on my little office chair. That's your RMR, right? That's the minimum amount required by like keeping your body alive, right? I'm sorry, that's your BMR, right? Conked you on the head, you're in a coma. Your RMR, no, god dang it, I got them backwards again. Sorry about this. Your BMR is the minimum amount in like an active state, and your RMR is the minimum amount when you are at rest. So if you're in a coma, that's your RMR, but your BMR is a much more accurate representation of how you live your life. You know, if you're sick in bed, but you're sitting upright, you know, maybe you stayed in bed all day, went to the bathroom once or something, but just, you know, your mom brought you soup all day, you know, that's your BMR, right? We are typically going to use the BMR when we are describing things because it's very, 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 very difficult to like measure someone's RMR. They have to actually be at rest. So typically we're going to use formulas in order to record this, but there are actual physical machines that can test your metabolism indirectly. They can basically look at how much oxygen is coming in versus how much CO2 is going out. And then based on like other more accurate formulas, they can use that to figure out how many calories you burn each day. And so that can also tell you whether or not you have a fast or a slow metabolism. So all of this is used in order to generate ATP, which I'm not going to put in your notes again. But adenosine triphosphate, right? An adenosine molecule with 3 phosphates attached to it. You know, the amount of that you are creating every day is determined by like the rate, right? What is your metabolic rate? Do you have more mitochondria? Do you have more cellular glycolysis going on? You know, what's actually generating your ATP? Now we do have some other chemical sources of energy as well. We also have ADP. Typically, this is a burnt up ATP molecule that has 2 phosphates instead of 3. Your body still can burn down that phosphate. It's just not going to get quite as much energy. And you got AMP, which is an adenosine monophosphate, which also has a little bit of energy, where the phosphate is attaching to the adenosine molecule. If you kick off that AMP molecule, you are left only with the adenosine. And now that adenosine is going to bind to receptors in your brain, and that's what's going to make you tired, which is where our conversation on caffeine came from yesterday. Looking at the parts of your cell, I'm also not going to do too much on this. You have your cell membrane, which is the outer portion of your cell. Its job is to, like, you know, if it needs to split up, it can in order to like divide, or it can also, primarily its job is to provide like a barrier to keep certain materials in and certain materials out. That's how you keep your organelles inside of the cell and keep all the fluid and other materials out. Now, that fluid on the inside part of your cell, we're going to call that your cytoplasm, okay? That's the interior portion of the cell that is all of the fluid itself, which we call cytosol, and all the organelles suspended within it, right? That is that. Now, your organelles, those are all the little things that do work inside of your cell. Like, your cell is like a little miniature version of you. It's got its own digestion ability. It's got its own like energy producer. You know, it's got its own little functional brain that does stuff. You know, it's just like you, right? A more accurate description, like, I love this. This is actually, like, I'm not a big on conspiracy theories, but I do love, and this like might sound like I'm getting like deep and you know, conspiracy or spiritual, but I love the fact that like the way that we organize, like the way we've organized our world is like an example of how like the universe organized us. Like, we have cells, which are like a membrane, kind of like your skin, with like a brain inside, kind of like your nucleus, right? And like energy producers, kind of like your digestive system and like metabolism, and then like a digestive system like your lysosomes, all these little things. And then we live in cities, which have like a power plant and like a police force and like a city like boundary and like roads to travel on and like, you know, places like grocery stores to pick up energy. And then like that city is part of like a country which has like a border, which has like states, you know, like, and then that's like all on a planet which is circling a sun. Like, and then that, you know, like, it's really funny to me that like all of that is like arranged in the same order every single time. There's your, you know, getting weird talk for the day. I got to do at least one weird thing every day. So all of the organelles that you have that do different things, right? Those are basically like the organs of your cell, and they have different processes. Lysosomes are in charge of like digesting stuff and, you know, eating anything that's like a foreign invader. Ribosomes are in charge of like assembling proteins, you know. And then the most important, arguably, is your mitochondria, right? Your mitochondria are the ones that are in charge of producing all that ATP. So the way that's going to work, right? You've got all of your blood here, and then here's like an example of like a muscle cell, right? So what's going to happen is like maybe a macronutrient such as a protein or fat or a carb goes in. If it's a protein, it'll go through gluconeogenesis and it'll become a carb. But any of those macronutrients come in, typically it's going to be these two. If it's carbs, it can go through your anaerobic energy system, or it can go through your aerobic energy system. If it's a protein, it's going to get converted into this, but that's going to go into this version here, so it'll go into the aerobic energy system. Your body doesn't use proteins for anaerobic metabolism. It doesn't use gluconeogenesis because it takes so long, it doesn't really have time to do it in this system. It only does it in this system. That's another reason why cardio kills your gains with a Z, by the way. Theoretically, although that's still not true. And then we have our fats, right? Your fats are also going to go through the aerobic metabolism, not the anaerobic. Carbs are the only ones that can kind of go through both there. So what's going to happen is like you've got your energy pool here, and that's going to create a bunch of ATP, right? And then that ATP is going to be outputted by your cell and get used in order to do stuff, right? Do all your work. Meanwhile, you are spitting out As a byproduct, some of the lactic acid is leaking out, some of the water is leaking out, but primarily you are excreting CO2. You're getting rid of it. So our energy systems, as a quick review here, you do have your phosphagens. Oh, and by the way, if we go back to this chart, your phosphagen system, that's basically just your ATP. It's just kind of, I love this. I actually love this chart. I should have pulled this up when we were doing energy systems because this chart is so good. But you can actually see your ATP pool here. It just kind of goes back and forth between the phosphagen system, right? Like it's like you have a bunch of Legos and you attach it and you break it and you reattach it and you break it and you just a whole bunch of this. So that's your phosphagen system. It's not really, you know, you'll notice none of the macronutrients are actually creating, they're not going into the phosphagen system. It's just kind of using busted up molecules of ADP. And then that ADP is like, I'm free. And then your phosphagen system's like, no, you're not. Creatine, poof. And now you have a new ATP molecule. So that's all resulting in, you know, kind of how this works. And then that all gets carried back by the blood. So your energy systems that you've got that phosphagen system, like we just mentioned, right? That's the one that creates ATP by using creatine to reattach it. You've got your anaerobic system, which is going to be glycolysis. That's producing ATP in the cytoplasm, in that lack of oxygen environment, the fluid portion of your cell. And then you've got your aerobic metabolism, which is doing it in the process, in your mitochondria, and it's using oxygen in order to be able to do that. So if we look at like the level of complexity here versus the amount of ATP production, your phosphagen system's super simple, right? It's like you've got ADP, you got creatine, well, you got ATP, right? Simple, super fast, very explosive, right? Which is great because that's another example. Here's another weird, you know, love another spiritual moment here. Your ATP system, right? It's short, it's fast, it's explosive, and that is exactly how you lift in order to target your ATP system. You lift fast, heavy, and explosive. And that's your ATP system. Then you have your anaerobic system, which is, well, also part of your phosphagen's also anaerobic. But you have glycolysis, right? Glycolysis is pretty simple, right? It's not really all that complex. And it's fast. It produces like, you know, it's a really close second to like how quickly ATP is being produced in your phosphagen system. But it's resulting in lots of lactic acid as well, which will then go through aerobic metabolism, which is crazy complex. You get that entire Krebs cycle, you got that entire electron transport chain. Both those things are pretty freaking complex. There's a lot of processes, there's a lot of steps. So it produces ATP very, very, very slowly. But the benefit is that it produces massive amounts of ATP. So how long does it take you to target these energy systems? Well, if it's your phosphagen system, your ability to make ATP with that system is super limited. You are pretty much going to run out of that ability in about 5 to 15 seconds. So the lag time, go back. The lag time, there is none. It is instantaneous, right? You want ATP, you got it, right? But then you have your anaerobic system, which is pretty limited to make ATP. If you are just the king of it, right? If you are Arnold Schwarzenegger, if you're great at staying in your lactate threshold, you can maybe stay in there for about 2 minutes. But in general, guys, it's about 30 seconds for the average person. And then you're going to start kicking over into your aerobic metabolism. So there is a little bit of lag time there, right? You have to get through that phosphagen system first. This is basically like, 10 seconds up to, sometimes I think NASM likes to quote it 10 to 50. That's like the glycolysis system. Most people will say like 10 to 30. And then you've got your aerobic system. Its ability to make ATP is essentially unlimited. You've got plenty of fat stored on your body, and you've got plenty of protein stored on your body. Your body can convert that protein into carbs and continue aerobic metabolism pretty much forever. There's no way that you are going to burn all of the energy that you have up. You would literally disappear. You'll totally pass out before that happens. Now, the lag time for this to happen can sometimes be up to 2 minutes, right? Like this can be a very long lag time sometimes. So there is like, the more quickly you can get into your aerobic metabolism as an aerobic athlete, well, that's great. But if you're trying to remain like an anaerobic athlete, you want to keep that, you want to make that last as long, you want to make glycolysis last as long as possible because that's associated with that high intensity. All right, so looking at ATP demands, like kind of what I'm talking about here. I'm gonna move this closer to my computer. Looking at these ATP demands here, if we look at your aerobic system, right, during like different sports and stuff, this is gonna use this is gonna make ATP using oxygen as well, right? So it needs those other systems to happen first in order to be able to kind of wrap it up with your aerobic system, right? So you can kind of see, this is that chart that it's a different looking, but it's the same chart that I pulled up in class when we were talking about intensity, right? So this is like where your ATP is coming from versus like your duration and intensity, right? So in the beginning, all your energy is coming from your phosphagen system. And then you move into your anaerobic energy system like glycolysis. But then glycolysis is going to start to die down as well. And that's where your aerobic metabolism has been kind of amping up this entire time. And then it starts to take over until finally your aerobic system is responsible for literally all of your ATP production. Okay, but you'll notice the intensity goes from very high to very low. If your aerobic metabolism is supplying all your energy, your intensity is very low. If your anaerobic metabolism, if your ATP-PC system is supplying all your energy, your intensity is very high. And if it's glycolysis, it's right in the middle. It's high to moderate, and it's supplying most of the energy there. So glycolysis kind of acts as this like a little stopgap between these two, kind of intense systems. So your metabolic pathways, like we've talked about in the past, right, they are organized to be able to do that. You're going to start anabolically with no oxygen, right? And then you are eventually going to switch into your aerobic metabolism. Oh, which is funny, but that's actually not even what I'm looking at on the slides here. I was only reading, I looked at the bolts. I wasn't actually reading what I was supposed to read. Talking about building stuff or breaking stuff down. Hold on one second, guys. This is distracting me. There we go. Oh, now I look like I'm an anonymous. I have hacked your computers. Looking at either building something up or breaking something, good Lord. Building something up or breaking something down. I guess that'll work. This is where you have either your anabolic pathways or your catabolic pathways. So back to the notes finally after a big long break. You have anabolic pathways, which are sort of what we're all aiming for, but this requires energy and results in the formation of complex molecules. Right, so anabolic metabolism takes simple things and builds them up into more complex substances, right? Versus catabolic pathways, such as exercise, which reduce compounds to form from being something simple. From being complex into something simple, right? So catabolic metabolism breaks down materials into their base parts, right? So your catabolic metabolism, digestion's a very good example. Your anabolic metabolism is like building muscle. But you know what's funny? Working out is catabolic. You're damaging your muscles. I went for a run earlier today, beat myself up, right? Like my body got all beat up. And then afterwards, I drank a protein shake to hopefully fuel anabolic pathways afterwards, right? So here's what we're kind of seeing here. These are different versions of catabolic reactions. So taking glycogen and breaking it down to glucose and energy, that's catabolic. Taking a triglyceride and breaking it down into glycerol and fatty acids and a whole bunch of energy, that's also catabolic. Taking a protein and breaking it down into amino acids, that is also going to be catabolic. But taking glycogen And I'm sorry, I'm looking at this upside down here. Taking two glucose molecules and adding them together to create glycogen, that is going to be anabolic. Taking some glycerol molecules plus some fatty acids and then turning those into triglycerides to store in your fat tissues, that's also anabolic. And then our favorite version, taking amino acids and building them up into new pec muscles or ab muscles or glute muscles or arm muscles. That is going to be an example of anabolic reactions as well. Here's the process of anaerobic glycolysis, right? In a nutshell here. This is just kind of another interesting chart to kind of highlight this a different way. But you got a molecule of glucose, and that is going to be breaking that down, actually use a little bit of ATP in order for that to happen, which then gets broken down into pyruvate. Meanwhile, a bunch of NAD and FAD are kind of flying off there. Those are going to be used later in the Krebs cycle. That pyruvate is going to ferment in this lack of oxygen environment, and then it will become lactic acid, which will then go through the Krebs cycle. And so that lactic acid will become acetyl-CoA, which will then kind of break off and kick off this whole process here. Your body's going to use a whole bunch of B vitamins in the form of like citric acid and oxaloacetate, which is freaking impossible to say, dehydrogenase, blah, blah, blah. All those different little enzymes there to cleave off a whole bunch of those NAD and FADs. And those NAD and FADs will eventually go through the electron transport chain here, and they'll all get squeezed into this little protein called ATP synthase or ATPase, where it'll squeeze it all together and leave you with a whole bunch of ATP. Meanwhile, both of these processes require oxygen to also come in as an ingredient. Now, this is a kind of a fun slide. If you ever want to take a closer look at this, this is actually how your body makes glycogen. So this is glycogenesis. It's kind of fun, actually. But basically, you got a molecule of glucose, and it can kind of go in both directions here, right? And then it actually like uses broken down glycogen to go straight through that Krebs cycle with the use of aerobic glycolysis. So this is the type of glycolysis that is happening across the cellular membrane. And that, guys, is the final review of metabolism. It will come up one more time next mod, but we've killed it. We've officially killed metabolism. What we are gonna transfer from here, rather than talking about ATP for an hour every day, freaking mouse battery is dying and is driving me crazy. Rather than talking about that every day, we're gonna start talking more and more about these numbers, your basal metabolic rate and your resting metabolic rate. Like if you burn 1,300 calories at rest, how much energy do you actually burn on days where you live your life? Or how much energy do you burn on days where you work out? Those are gonna be different numbers of energy. And so I gotta warn you now, math is coming. We've got, for the record though, I will say it is as simple as doing this in the real world. I just make you do, this is like an evil trick that NASA makes me do. I will make us do the formula versions because that's a really good way to get you to memorize the names of the formulas, which is what you'll be tested on. They won't make you do math in the NASA. They can't, right? It's a multiple choice test. And it's not like they're going to be like, you know, multiple choice, like your client's resting, you know, age is this and their something is this. What's their metabolism? And you've got to do this giant ass equation. They won't make you do that. That would be insane. But they will say the blank is a formula used to calculate metabolism. And the answer to that is the Harris-Benedict formula. So I'm going to make you do the Harris-Benedict formula a couple times so that you know how to do it and memorize the name. You do want to get a little bit used to it, but I will say you can just simply do this. Harris-Benedict formula calculator. Click, enter numbers. $1,860 per day at rest. Okay, so that's by default. If I were in a coma, I would be burning 1,860 calories per day. So now I got to take into account, look at that quarantine activity. What the heck are we doing? Now I take into account Harris, Benedict multipliers. And by the way, there's the formula. So now you can take into account your activity factor, right? Are you highly active? There's all the different formulas. If you're sedentary, well, you're going to take that number and you're going to multiply it by 1.53. What was the number? 1860. So if I'm resting, let's say I'm just hanging out at the house, it's Sunday, it's my rest day, right? 1860 times 1.53, 2,800 calories per day when I'm at rest, right? Let's say I'm not at rest though. Let's say I'm working out, right? Let's say I'm, running an hour a day, which I'm not running an hour a day, but I'm lifting weights an hour a day, right? So now I'm going to use the BMR of 1.76. So I take 1860 times 1.76, and that's about 3,273 calories per day. And that's about how many calories I try to eat every single day. Unless I'm trying to lose weight, in which case I will eat less, or unless I'm trying to gain weight, in which case I will eat more. And that is how that works. That is where we are headed for the rest of nutrition and for our weight loss class, program design class, which is coming up. So, big day. You made it through metabolism. Maggie, how did you get on top? How did you get above me? That's not supposed to happen. What did I do? So during digestion, carbs are broken down into monosaccharides, and then they absorbed into the body. That monosaccharide that we generally talk about is glucose. Digestion of fats is going to begin in the mouth, but then it will end in the small intestine with that bile by breaking it down into free fatty acids. And then absorption of those fats is going to occur in the small intestine along with everything else being absorbed in the small intestine. Proteins are also going to get broken down primarily in your stomach, as well as a little bit in your small intestine. And then once that's broken down into amino acids, it can officially be absorbed by that small intestine. Your minerals, your vitamins, and your water don't need to be broken down. They can be absorbed directly. Vitamins do need to be carried by either fat or water in order to actually make it into your bloodstream. And then we have our three main energy systems for creating ATP. Carbohydrates are the ones that we prefer to metabolize anaerobically, but we do have our aerobic systems, which are a little bit better at burning fat for fuel, and aerobic glycolysis, which are good at burning glycogen for fuel. And that's basically that. All right, do you guys have any questions tonight? Anything that I breezed over really quick that you're worried about?
No, not really.
Well, heck. All right, guys, I'm gonna kick you out of here. I'll see all y'all tomorrow.
All right, Brad. Take it easy.
Oh, by the way, are you going to email this?
Yes, yeah, it's gonna go up now. This is the recording. So you'll get the daily email and you'll get the homework in about a half hour.
Okay, cool. Thank you.
No problem. All right, see you guys.
All right. Bye.